Thank you for the warm welcome and welcome to my talk on Apache Hadoop. It will be a talk on large-scale data processing, which is basically a very hot topic currently. But first of all, I would like to explain who I am. My name is Isabel, just as announced. I'm the organizer of the Berlin Hadoop get-together, and I'm co-founder of Apache Hadoop. What is Apache Hadoop? Yet another name. Hadoop is a library that intends to implement machine learning algorithms that scale. Scale in terms of community, have a vibrant community, have very lively mailing lists. Scale in terms of has a commercially friendly license, and of course scale in terms of scale to large data sets, to huge amounts of data to train on. In order to reach the last goal, most of our algorithms currently are based on Apache Hadoop and are implemented on top of this framework. And at daytime, I'm a software developer in Berlin. Now I would like to know a little more about you. Whoever has seen a talk by me and knows that I'm doing Hadoop get-togethers in Berlin knows that usually I take this microphone and give it to the audience and ask you stupid questions. But as there are so many people here, I'll just do it a little differently this time. Please, would you raise your hand if you know the term Hadoop? Oh, that's awesome. How many of you are actually Hadoop users? Okay, good. Next question, how many nodes does your cluster have? 10 or more? 100 or more? 1,000 or more? Okay, good. So some more buzzwords. Who knows about Zookeeper? Okay, quite some people. Anyone aware of Hive? Some more. How about HBase? You should know about that one. There was an interesting talk at the NoSQL Dev Rooms this morning. Anyone aware of Pig? I mean, not the little animal, but the project, actually. Lucine, I want to see all your hands. Okay, Solar. Any Solar users? Great. Anyone know about Hadoop before I told you about it? Anyone using it? No one? Yeah, there's someone. I want to talk to you after my talk. Okay, what am I going to go and talk about? First of all, we have a chapter on collecting and storing data. Next chapter will be on analyzing data. I will give you a short tour of Hadoop, tell you what's coming up, tell you a little bit about the history, and last but not least, there are a few slides on the Hadoop ecosystem, because whoever raises hands during the questions I just asked you knows that there is not just Hadoop, the core project, but there are many satellite projects that make working with the framework easier. Okay. Collecting and storing data. If we go the traditional way and have a look at where data is collected, we may come up with an example like that. We have a shop, we have products in the shop, and we want to collect information on how many products do we have, which price does each product have, how many products did we sell, information on our customers, where do they live, and so on and so forth. First solutions that comes to mind is regular relational databases like MySQL, Postgres, or Oracle. Store the data in a relational model, analyze the data, maybe put it into a data warehouse, maybe run OLAP queries over it. But what if the data that I have is not really relational data? What it's maybe a bunch of log files? Say transaction logs from your regular web shop, or say something like query logs. If you're running a very successful search engine, you may want to track which queries users are actually searching for to improve your system. And what if those log files scale to the point where they don't fit to your regular hard disk anymore. So you end up with data that cannot be stored on a single machine, and you end up with data that cannot efficiently be processed in a serial way. The logical consequence would be to use multiple machines to process your data, maybe to build a little cluster, distribute computations, use a distributed file system, and just go with that. There are a few challenges when doing it this way. First challenge is you are all computer users, you know that single machines tend to fail. The MacBook I'm using here to give this presentation had a hard disk failure 12 hours before I gave my talk at Hadoop User Group UK last year. So I was pretty happy to have a backup of my presentation. If you have not only a single machine, but like a data center with multiple machines, each machine you add increases the probability of any of those machines failing. So what you want is a framework that gives you built-in backup, built-in replication, and built-in failover. Now you need someone to write programs to analyze the data. If you have a look at typical software developers, usually if they come out of university and are not as brilliant as FOSDEM visitors, they never have dealt with large amounts of data. So they don't know how to handle petabytes of data and don't know all the intricacies that come into play when writing parallel programs. And usually for a project, you don't have time to actually make software production ready. And with production ready here, I mean something like it has defined failure modes, it has failover if a machine crashes, it has defined error codes if something goes wrong, and so on and so forth. So you want something that is easy to use, basically something like parallel programming on Rails. And if you're thinking about using an open source framework, you want something where bugs are regularly fixed, where new features are added, and where your patches are integrated into a system. So you want something with a vibrant, lively development community. And last but not least, the guy between you, the developer, and your customer is an operations guy. And I think I may promise you that he's going to yell at you if the system isn't easy to administrate. And he'll probably also start yelling if for every single little application that you write, you're using a different framework. So you need something that is easy to administrate, and you need something that is kind of a single system that maps to quite a lot of tasks that you want to solve. That is when you may want to have a look at Hadoop. It's easy distributed programming. So for me as a developer, it makes it easy to write distributed applications without a very, very deep background in parallel programming, distributed cluster programming, or HPC. It's well known in industry and research. It's used by companies like Yahoo, it's used by Facebook, it's used by the New York Times, by Last.fm, and many more. And it scales well beyond 1,000 nodes. So where does that funny little project come from? What is the history behind it? Well, you may have heard of the MapReduce implementation of Google. That was done in 2003. At about the same year, a paper was published by Google on a distributed file system, GFS, and another year later, the MapReduce paper came out. It didn't take very long until Doug Cutting, the original author of Lucene, reported that Nudge, which is an internet-scale search engine, makes use of MapReduce. It didn't take long again to grow, for the module to grow so much that it rendered an extra project beside Nudge. In 2007, Yahoo reported running a first Hadoop cluster with 1,000 nodes. And like 2 years ago, it was finally its own top-level project at Apache. So last summer, just to show you that the framework really works, Yahoo has won the petabyte sorting benchmark with a Hadoop cluster. So what are the assumptions that are underneath the frameworks that you should be aware of if you're writing Hadoop applications? First assumption, as I already mentioned, is that the data does not fit on a single node. What comes out of that is that we want to use commodity hardware, so we don't want to use the PC that's underneath the desk of your secretary. It's still kind of beefy, strong hardware, but it's not dedicated. It's not a dedicated hardware. What comes out of that is that failure happens. The idea is to distribute the file system, to build replication into the file system. Built-in replication means that every file that is stored in the file system is replicated by default 2 times, so it's available 3 times. And you have automatic failover in case of failure. Second assumption is that you have so much data that it's pretty expensive to move the data from where it's stored to where it should be processed. So the idea is to turn the whole model around and move the computation to where the data is, and keep computation local to data. Third assumption is, well, disk seek is very expensive compared to continuously scanning files. So the APIs that you have available in Hadoop focus on making scanning data very easy, but they don't make it easy to write applications that need random access to your data. So you need to reformulate your algorithms such that you can stream over the data. If you go to the website, hadoopapache.org, and download the package, basically what you end up with is 2 kind of components. One is HDFS, the distributed file system, and the second is the MapReduce engine. We'll have a look at each of these in the coming slides. First of all, the distributed file system. If you install that on your little cluster, what you end up with is one node called the name node, holding file metadata. That is, each file basically is split into separate blocks, and the name node keeps information on which node each of these blocks is stored. Besides that, you have several worker nodes called data nodes that actually store the data. So basically, you could compare the name node to holding sort of the inode table of your cluster. What this means is, okay, our name node stores file metadata. It stores that metadata in memory, and it stores a mapping from file blocks to actual nodes. So that means, if you store that in memory, this means that the size of your cluster depends on how much main memory you give to your name node, and it depends on how large you make each file block. If you make the blocks large, you can store a lot of data because you don't have so many blocks per file. If you're writing a program against HDFS, how does writing a file look like? Let's assume you write an HDFS client that runs on a client node. Logically, first thing it does, it goes to the name node, tells the name node, I want to create a file, and the name node tells it, okay, so you can go, the file should be stored on this data node. After that, the client goes to the data node, stores its data, and as I mentioned earlier, the system has replication built in, so the data node goes and pipelines the data to sort of slaves. After replication is complete and all is written to the system, your method call will return. The replication strategy that is used is basically a trade-off between bandwidth that you have between nodes and between distributing your file evenly across the cluster in order to minimize failure spreading. You don't want all 3 replicas on one hard disk, obviously, but maybe you don't want them in one rack as well. So if you have a look at an example, we may have our client on the left-hand side. To optimize bandwidth, this client may write to its own data node. This one replicates to a different rack, and on this rack it's again replicated to a different data node. File read looks similar. You have your HDFS client. It talks to the name node and tells the name node, I want file X. Name node tells my client, okay, this file is distributed across these data nodes. It goes to the data nodes, reads the blocks, and gets the information. So now you know how to store the data, you know how to read it back, you know how to interact with the file system on a sort of coding level. But what you really want is write programs that analyze your data in order for you to deduce information from it. So that's where the MapReduce engine comes into play. To explain what MapReduce is all about, how many of you have written MapReduce programs? I should see, yeah, quite a fair amount. Okay. Okay, one example. Takes this little XML file. It doesn't look very pretty. It's just a snippet from the RSS URLs that are in my RSS feed reader. Goal would be, of this task would be to read the file, extract host names of each block, and extract the top 10 host names of blocks that I read. If I were to do this on a standard Linux machine with regular tools, I would do something like that and come up with a list of, okay, there are like 10 RSS feeds from archives, there are 6 RSS feeds from Google, and so on and so forth. If you have a closer look at how that's done, it would probably look something like that. You define a pattern that kind of looks like a host name. No guarantees this is the right regular expression for a host name. It's just for the example. You would grep over the file. You would then sort by host name, and finally count how many unique host names you have in this list. If you map that over to MapReduce, what you end up with is a map step for grepping over the files. You have a reduce step for counting, and what the framework does is the shuffle phase. Basically, your map function would look something like read a block of data. Remember that in this case, this is not a kind of feed URL file that is just a few megabytes in size, but maybe 1 petabyte, 1 terabyte. So it may be distributed across the cluster. So our map function is run exactly on those nodes holding the correct fractions of our data. Map function then extracts key value pairs, where keys are the host names. Value may be, for instance, how often did I see this host name in the current block of data. If I write the reduce function, I have the guarantees that I see all key value pairs of one key type for one call of the reduce function. So summing up is very easy. I just iterate over all the values and put out key and sum mapping. If you have a closer look at what this may look like, it's something like that. I read the data from the HDFS. I have multiple map tasks run all over the cluster. Each of these map tasks outputs key value pairs, in this case host name and counts. This intermediate output is shuffled and grouped by key. And in the end, I have reduced tasks that compute the final results. If you have a look at the Java API, it may look like something like this. If you are used to sort of the old API of Hadoop 0.18, this one is a new one, It's a lot cleaner and more compact. In the map function, again, you get a key value mapping. In this case, it may be something like file name and content. You iterate over the content and extract host names. And the context object gives you a way of emitting key value pairs. What the context object gives you as well is a way of emitting sort of counter values. Counters can be used, for instance, to provide the framework with a number of bad records that you have encountered. So you just skip the record and keep a statistic of how many bad records were in the file. But the context also gives you a way of telling the frameworks that you're actually progressing. Because what Hadoop does is, if your job is running for too long, then it cannot really decide, are you in a endless loop or are you really doing work? So you can set up a timeout after which the job is killed. So like if I don't see progress updates for that many minutes, seconds, whatever, kill the job. Which of course is bad if you have a long-running mathematical job. So you want to tell the framework, oh yeah, hello, I'm still alive, I'm not dead, and I'm doing sensible work, so please don't kill me. The reduced job then simply sums up the values and outputs the result. If we have a look at our little picture, for MapReduce, we now have a special node called the job tracker. That is the node that we connect to submit MapReduce jobs. And we have on each slave node task trackers that really run the map tasks and the reduced tasks. What does a MapReduce job really look like? If I write my client application on my client node, this application contacts the job tracker and tells it, hey, I've got a job for you to run. Job tracker then has a look at where the data really is located, contacts the machine. On that machine is a task tracker. This task tracker is responsible for scheduling, for local scheduling. What the task tracker does, it starts a JVM on this node, runs the map job or the reduced job in this JVM, and returns its output. Why does it run in a separate JVM? Well, as I told you, the framework should be robust, and being robust means that client jobs that are run shouldn't crash the whole framework, and it even shouldn't crash a task tracker. If I have a client job that crashes my client JVM, I want it to be in a separate JVM. So this also means that if I run MapReduce jobs that are very, very short, that there is quite a bit of overhead. But the assumption is that really I have that much data on my node that the overhead of starting another JVM doesn't count so much. And of course, again, you have not only one task tracker, but multiple of them. So if you were to start your own Hadoop hacking, what do you need in terms of hardware? In terms of software, it's easy. You go either to your Apache Hadoop website and download the Hadoop distribution, or you go to Cloudera, use their Hadoop distribution, or you go to Debian. People had some package up Hadoop for Debian. There are people working on it at the moment, so they have Hadoop in the pipeline, so it may not be long before you can just type up get install Hadoop and get your system up and running. But what do you need? Probably this is the dream of everyone, right? Running it in a data center on thousands of nodes, just happily hacking along. If you don't have a data center, you may use other people's data centers. Anyone not aware of EC2? Okay, so you just run machine time from Amazon. You can get your own Hadoop cluster up and running on EC2. There are a lot of how-tos, and there are also AMIs that makes that very easy. If you just want to play around, there's MapReduce as a service at Amazon. It doesn't use HDFS, but its own backends. but it's pretty nice to get started and get playing around with MapReduce in the first place. However, be careful because Elastic MapReduce uses the sort of old MapReduce API, not yet the new one. If you don't want to go into cloud computing, you can set up your own little Hadoop cluster, thanks to Tilo for installing the Hadoop cluster, and thanks to Packet and Mask from the CCC Berlin for providing some of the hardware. But you really don't need large servers. Actually, you can start playing around with just a tiny little laptop like the one over here. You can run Hadoop in sort of single node mode, in sort of pseudo-distributed mode, and get your programs run locally. This also is very handy if you want to debug programs, if you want to develop new stuff. Then you probably want to try it out on your development machine. You don't want to go to your cluster and fire up the debugger and debug in a distributed way. You want to do this locally on your machine, probably even within your IDE. So what is up next? Next up in the 0.21 release, there will finally be append in HDFS. So far you can write files and you can close it, and that's it. The goal is to facilitate opening files again and appending to the end of it. It's a pretty long story of getting append into HDFS. And there will be more advanced task schedulers. In 0.22 there will be more security. Currently there are sort of user rights, but there is no real hard security on data on the cluster. So the basic assumption is it runs in your data center and there it's safe. There will be Afro-based RPC, so that RPC is compatible across Hadoop versions. Anyone ever heard of Afro? Hey, great. Afro basically is a RPC and serialization library that is a sub-project of Hadoop and written by Doug. There will be symbolic links, and there will be federated name nodes, no more single name node. So who's using Hadoop? We may hear a little bit about it in the next talk by Facebook. Hadoop is used by Yahoo for lots of analysis. It's used by Last.fm for coming up with recommendations. It's used by the New York Times for scaling images and converting images. It's used by search engines like DeepDive for text analysis, and it's used by several search engines that are based on Nudge or on Kata. So if you have a look at Hadoop at a broader sort of scale, there's not only the core project, but several people working on other projects that make it easier to handle Hadoop, that make it easier to write MapReduce jobs, that make it better for data storage. Let's first have a look at higher level languages. Some of you may know some of the logos. Just to motivate why you need higher level languages, I'll give you an example. I'll take the example from PIC. I am taking it from PIC because I saw the presentation on PIC 1 year ago, and they had a very, very great example motivating why you need something like a higher level language. So suppose you have some user data in a file, you have website data in another file, and you want to find out the top 5 most visited pages by users aged 15 to 25. Sounds like a pretty reasonable task to do, isn't it? So you need something to load your users, load pages, you need something to filter users by age, you want to join both on name, you want to group on the URL visited, you want to count the clicks on each URL, you want to order by click amount, and you want to take the top 5. If you were to do this in Java code, it would look something like that. You're not supposed to read it up there in the last rows. You're even not supposed to read it over here in the front. If you're doing it with pig, it looks like something like that. And I hope that even the guys over there in the back can read it. So what you can do with it is write pretty easily one-off jobs for data analysis. Of course, you pay some overhead when running these jobs, but then again, you don't have to write hours, loads and loads of Java code. And it's easier to understand, of course. There are some projects making it easier to distribute storage. As I explained, HDFS is not optimized for random access. It's optimized for continuous files. So what if you want sort of kind of random access, and what if you have semi-structured data? Then you may want to go for HBase, or you want to go for Cassandra, or you want to go for Hypertable, which are all three based on HDFS. There are a few libraries built on top of Hadoop, and there are a few libraries that make handling your data easier. You may store your files in a plain text format, but that obviously isn't very efficient. Neither space efficient nor time efficient in terms of parsing time. What you want is sort of a binary format, but you want a binary format that you can upgrade easily. That's where something like Afro or Thrift or Google Protocol buffers come into play. Then a lot of innovation happens around Hadoop. As I mentioned already, there's a project building machine learning algorithms on top of Hadoop. We have clustering algorithms for grouping items by similarity. We have classification algorithms for classifying new incoming items into predefined categories. Well-known example is spam email classification. So we have two categories, mails that I want to have, mails that I want to throw away, and I want to learn a classifier that separates data points into these classes. That's what you can do with Mahout. And of course, you can do recommendation mining. That is like if you go to Amazon and you buy a book, usually Amazon tells you people who bought this book also bought like these and such books. That's something you can implement with Mahout. And of course, there are also search engines that are making use of Hadoop to distribute indexing. So I've done a lot of advertisement for Hadoop, just 3 final slides of advertisement. Why should you go with the project? First of all, it's proven code, it works in practice, it works in production, and you don't need to reinvent the wheel. Next, it's an Apache project, and there are mailing lists that are very lively discussions on the mailing lists, people who are willing to help you. So come to the mailing list if you're a Hadoop user and provide input. By the way, if you're a Mahout user, the same applies to you. Last but not least, it's very well possible to become part of the community. If you have a look at the graph here in the bottom, that's just the growth of emails and on the all Hadoop mailing lists. So the community is still growing steadily. And there are people from inside as well as from outside Yahoo, people working full-time, people working in their free time on Hadoop. So final advertisement, if you're using Hadoop, come to the mailing lists, talk to us. One advertisement in my own interest, I'm doing the Hadoop get-together in Berlin. Next one is on March 10th. If you need an excuse to visit Berlin, there will be 3 talks after 5 p.m. There will be beer after the event. There will be lots of interesting discussions and lots of interesting people there. And there's another Hadoop event in Berlin. Looks like this year is the Hadoop year for Berlin. There will be a Berlin Buzzwords event on June 6th and 7th talks on the topics storing data, searching, indexing, and scaling to large amounts of data are welcome. We welcome talks on Apache Hadoop, on NoSQL databases, on distributed computing, on business intelligence applications, on search applications, on scaling search indexes, and on cloud computing in general. So you already noticed that when I'm telling you all those names and words and tokens, it should be easy to play buzzword bingo at that conference. So that's my final invitation to come to the mailing lists. Thank you. Any questions?
Hi. I was wondering what is being done to make HDFS mountable as a regular file system.
Sorry?
How can you mount HDFS as a regular file system? Does that work yet? Or?
It works with Fuse.
With Fuse,
You can mount it with Fuse.
Okay. And does that work nicely, or is it like...
For me, it always worked, but you should be aware that it's not a POSIX file system, so it doesn't support all the POSIX standard stuff.
Hello, maybe I missed this before, but you were mentioning the Amazon Elastic. They had an old MapReduce API.
Sort of old.
So what's the difference, and what's the advantage of the new? And yeah.
The new one is more compact. It isn't so verbose, and the signatures of your map and reduce functions have changed a little. So it's kind of easy to port your jobs. It's not kind of sort of a very fundamental change, but you have to adapt to the new API.
I'm trying to follow up to that first question. I'm afraid I didn't hear your answer to it all that clearly. But what I'm wondering is, suppose I wanted to implement an stdio-like layer over it and be able to just save to Hadoop from my word processor, my image processor, whatever file I'm using. How far are we from being able to support that?
Sorry, I can't answer that question currently. Please guessing that is probably far away.
Sorry?
You're far away. I mean,
Can you just hand the microphone over?
from a POSIX file system, you're pretty much far away because you can't reopen files and then append. So you just can't. You can write once and then close it and maybe read it again, but not append. That's common.
You also cannot insert into files.
So
So
C
you
doesn't
it's
work.
really read once.
Well, it doesn't work now. But, so if you're interested to work on that, maybe you should think about being part of the project and not building a standard I/O layer on top of that. Because I mean, it would be way more efficient, wouldn't it?
Well, I kind of did check out HDFS with a view to looking at that, and then I thought, why not ask people who know before investing time in it?
It's definitely worth it. It's definitely worth it. Do it.
Hello. Hi. Simple question. You said the system is designed with failure assumed, but there seems to be a key dependency on the name node. What happens if the name node fails?
You should have planned for failover in the name node with your standard measures. So currently I'm not aware of anything in the framework itself that there is a failover in the name node, but it's sort of easy to implement it and design it into your cluster.
You mentioned Amazon's Hadoop on demand. I'm guessing they have their own API for that. And I don't mean the actual Hadoop API, I mean their customer-facing API.
You can write regular MapReduce jobs with the Hadoop API and submit them.
So there's no API. Amazon didn't implement its own API.
Basically, you can take, for instance, Mahout and run it on Elastic MapReduce. That has been done about 1 year ago.
Okay.
The only thing that you have to take care of is that the Amazon API is based on Hadoop 0.18, and that API differs from what is currently available.
There's got to be a web-facing API in front of that, right?
Yeah, sure.
That is Amazon specific?
Yeah.
Are there plans for an open implementation of that API, the web-facing API? And Hadoop on-demand web API? Is that of any interest?
I think it's currently not on the schedule, but you can ask on the mailing list for input on that.
Excuse me. Yeah. I have a question. Does the Hadoop framework support backing up my data store in a consistent way and restoring it in any way?
It does have backup built in terms of replication. So each file you store to Hadoop is replicated to 3 hard disks. And in case one of those hard disks fails, in case one of those nodes fails, replication is started again to get up to the target level.
Is there a way to just take a backup for maybe today, 12 o'clock, and to restore it completely?
If you really
file
want
space?
Do you really want to do backups of petabytes of data? Do you have that much storage available?
No, if you have for our applications, there are requirements legal requirements to be able to restore at a certain point in time, and we looked at Hadoop and didn't find a way to do a point in time backup and restore.
I mean, you can always read data from the cluster. No one's stopping you from doing that.
That it's not that I can't freeze my cluster at a certain point in time. I can freeze a machine, but not I didn't find a way to freeze the entire cluster.
I think this is up to you to implement that.
Okay, so this has to be done in the application.
This is?
This is a job of the application and not of the cluster from your design. Thanks a lot.
So my question is about the fact that Hadoop scales on multiple nodes, but how does it handle multiple processors on each node?
Of course, jobs are distributed on multiple processors. But currently I'm not aware of any sort of optimizations in terms of this data I'm outputting in this reducer should be post-processed on the same node, because the node has multiple processors and it can do this in parallel. As far as I know, this optimization isn't in it. But of course, the framework makes use of multiple cores if you have multiple cores available on each node. It's perfectly reasonable.
Is it in which language Hadoop is written? Is it Java or C?
Main API is in Java, but there are bindings to write C++ programs as well. And there are streaming and pipe APIs so that you can use any scripting language of your choice. So if you really want to, you can write your data analysis jobs in Python, PHP, whatever you want.
So if I want to run it on an embedded system, it won't be possible?
You want to run it?
Like a small router that has Hadoop inside with, let's say, 32 megabytes of RAM won't be possible?
Sounds like a crazy idea.
Okay.
Are there any more questions? Please show.
If you just use Hadoop as a file system, do you have any comparative benchmarks with Lustre?
Sorry, again, please?
Do you have any comparative benchmarks with Lustre, the Lustre file system?
There should be benchmarks, but I don't have them in my head. You can probably look them up. If there are any more questions, feel free to contact me after the talk. I'm happy to answer any questions. And the guy over there who raised his hand on it, Mahout, please come to me and talk to me. I want to know more on your use case.
Are there any more questions?
Could you tell me what are the memory requirements for the HDFS nodes?
Depends on how much data you want to store in your cluster, and depends on the size of your blocks. I don't have exact numbers in.
Generally, is it a memory intensive task or?
Which is in memory intensive stuff?
Well, okay, you said that for the name server, it's required to have a large amount of RAM. But what about the nodes?
You mean for the name node?
No, not the name. Name node is a single entity that needs a lot of RAM.
Yeah.
And what about the nodes which are containing the data?
They don't need to be that. They are not that much dependent on main memory.
Okay,
it's mainly the name node.
Okay, thanks.
So we have still some time left. If you have any more questions, take your chance. Okay.
Just an announcement, because I saw somebody searching for Debian packages at Cloudera for Hadoop. Hadoop is in the pipe to enter Debian Unstable the next weeks.
I included that announcement, and I told people to help you get this started. So if you want a Hadoop package into Debian mainline, that's the guy to talk to. Could you please get up again? So people really need to help this guy, because I would like to have a Debian package to be able to type apt-get install Hadoop on my regular Debian machine without Cloudera repositories, without external repositories, just in Debian main.
Somebody to compile the C stuff.
Could you just give him the mic to...
I need somebody to help me out with the C stuff and all the bindings. I've done the Java stuff. This is packaged.
Here who can help him with Debian C stuff? Talk to him.
Okay.